Hello to all of you. This is Dr. Dhaval Maheta, and today we are going to talk about modeling the variance. That is GARCH model in EViews. The full form of GARCH is General Autoregressive Conditional Heteroskedasticity. In conventional econometric analysis, our assumption is that the variance of the disturbance term is constant over the time. This assumption is the homoskedasticity assumption. But it has been observed in many financial time series that they exhibit the period of unusually high volatility and low volatility. In other words, we observe that the large changes in stock returns seem to be followed by other large changes and vice versa. This phenomena is known as a volatility clustering. In such cases, it is very clear that the assumption of the homoskedasticity, that is a variance being constant over the time, is violated, and in such instances, it is preferable to examine the pattern of the volatility. The autoregressive conditional heteroskedasticity model was designed to improve the econometric models by replacing the assumption of constant volatility with the conditional volatility. Ainsley and others working on our models recognize that the past financial data influences the future data, and that was a definition of the term autoregressive. The conditional heteroskedasticity portion of ARCH simply refers to the observable fact that the volatility in the financial market is not constant over the time period. Ainsley's idea starts from the fact that he allows the variance of the residual sigma square to depend on past history or to have the heteroskedasticity because the variance will change over the time. Let us try to understand this concept by the small equation. Yt is equal to alpha plus mu t. So now if I make sigma t square the dependent variable, this dependent variable is you have to include mu square t minus 1 in the equation as the independent variable. So my sigma t square is equal to lambda 0 plus lambda 1 mu square t minus 1, this one, the square of the residual, which is a basic ARCH-1 process. Now in GARCH family, what's the difference? Let's try to understand. The originator of the GARCH model was Tim Berners-Lee in 1986. The simple mean equation which we had seen in ARCH family, yt is equal to alpha plus beta xt plus mu t. Now instead of sigma t square, we are going to replace this with ht. So now my ht is equal to lambda 0 plus theta 1 ht minus 1, its own lagged term, plus lambda 1 mu square t minus 1. The new term which is added in the GARCH model is theta 1 ht minus 1, its own lag. GARCH model says that the conditional variance h, or the volatility at the time t, depends on the past value of the shock captured by the lagged square error term, this one, and the past value of itself, that is ht minus 1. The assumption here is that the variable should be stationary. For stationarity, again, theta 1 plus lambda 1. Theta 1 plus lambda 1. Its summation should be less than 1. If in any case it is greater than or equal to 1, we will have to use the integrated GARCH model. The similarities in ARCH and GARCH family are both are used for modeling the volatility of the stocks. It captures the conditional and the time varying variance, deals with stationarity and non-stationary time series. It captures the volatility clustering. They are the mean reverting processes. It estimates the riskiness of the security. In GARCH-1 model, it should be very clear to the reader that if theta 1 is equal to 0, the model reduces to the ARCH family. Very clear? Let's go back. If I assume that theta 1 is equal to 0, our model will simply reduce to ARCH family. GARCH model tells us how volatility changes with lagged shocks, mu square t minus 1, and the momentum within the system via ht minus 1. The differences in ARCH and GARCH family are, the ARCH model was developed by Angel 1982. It is quite often difficult to use as it produces the negative betas. To resolve this problem of negative betas, Berners-Lee developed the generalized ARCH model, that is a GARCH model. It resembles more of moving average rather than autoregressive models. We don't have AR terms in it. It's just like a moving average where we are just considering the square of the residuals. It includes the lagged conditional variance error terms as an autoregressive term, that is HT, and its own legs are considered. There are q plus 1 parameters to be estimated. If q is very large, accuracy is lost. There are very heavy chances that the model will become over-parameterized. Here, usually few parameters to capture long-lived effects. Efficiency of estimation is quite improved and it gives us the parsimonious model. The conditional variance is a function of arch terms. Here, the conditional variance is a function of arch and GARCH term. It cannot capture the leverage effects. It can capture the leverage and asymmetric effects which are there in the series. Are GARCH estimates better than the arch estimates? Definitely. The GARCH estimates capture the higher order of the arch term as we have proved before. Therefore, it is better to estimate a GARCH instead of higher order arch model due to its easier estimation and the least possible loss of degree of freedom. If we make arch model with too many legs, it will become over parameterized, our degree of freedom is lost, and the coefficients will become insignificant. Moreover, it is found that the Akaike information criterion and the Schwarz criterion statistics in GARCH model are smaller compared to the arch model. So GARCH model is always preferred over the arch model. GARCH-1 model equates to arch-2 model. Therefore, GARCH-PQ model equates to arch-P plus Q model. There are 5 models for error construction which we can consider in GARCH models. 1. Gaussian normal distribution. Students T. 3. Generalized error distribution. 4. Students T with fixed degree of freedom. 5th. Generalized error distribution with fixed degree of freedom. Now let us see how we can do this in EViews. We will first of all activate the return series, view, graph, click OK. And you can see there is a very heavy volatility clustering which is happening. Strong evidence of volatility clustering. Now I will again go back in view, descriptive statistics, and histogram and stats. You can see here there are big fat tails here. It means that this normal distribution curve is leptocurting. Now I will go in estimate equation. Quick estimate equation. I'll write down here as returns C returns -1 and activate the arch family. Make sure arch 1 is on, GARCH 1 is on. Go in options and this time activate the EViews legacy. Click OK. You got the results. I'll simply copy this result in my Word file. Now here we have to see this two equation. This is a mean equation. Let me highlight this. This is a mean equation. And this is a variance equation. These are the terms of mu square t minus 1. And this is a term of ht minus 1, which we had seen on the model. Now how to interpret this? The returns is equal to the constant, this 0.00 plus 0.0625 into returns minus 1. The constant captures the mean return coefficients. It is positive and statistically significant. You can see the p-value is less than 0.05. So average stock return is 0.0043. And its past value are also affecting the current series by 0.063. This one. The returns of the past are affecting the present returns by 0.063. Now this is a variance equation. Here the coefficients of GARCH and arch parameters are positive. This you will have to see. Arch and GARCH are positive and statistically significant at the 1% level. The time varying volatility includes the constant, this one, plus its past 0.94 ht minus 1 and a component which depends upon a past error which is 0.05 1 mu square t minus 1. The above finding very well states that the presence of time-varying conditional volatility of the returns of the stock is present. The interpretation goes this way. The result also indicates the persistence of the volatility shocks as represented by the summation of arch and GARCH parameters as summation of theta plus lambda 1 is large. It denotes that the effect of today's shock remains in the forecast of variance for many periods in the future. Now, let us run GARCH 6 model. I'll again go here in estimate and I'll convert this thing into 6 and 6. Click OK. You got the results. Now here, this is a whole family of arch terms and this is a whole family of GARCH terms. So here the model is over parameterized, and as the model is over parameterized, what will happen is your p-values will become p-value is insignificant. They will be more than 0.05 and the coefficients have got the negative signs, which is not desirable, and therefore the predictive power of the model will decrease, which is not at all desirable. Now let us try with another model. I'll go in estimate. I'll make this as GARCH-1 model. 1 and 6, click OK. So here also you can see here many of the terms are having p-value more than 0.05. Moreover, they are having a negative sign. This means that the predictive power of the model decreases. Which model is better, arch or GARCH? Basically, we will have to draw a line. We want to include less variables in the model so that we get the parsimonious model instead of over parameterized model. In the comparison of two GARCH model, we will always compare the model on the basis of the Kaike information criterion and the Schwarz criterion. Again, we will come back to our base model, that is Arch1 and GARCH1. Click OK. Now I will make the GARCH variance series. Proc. I will compare the variance series from the Arch family and the GARCH family. So for that, I'll go in proc, make GARCH variance series, and I'll save this series with a name GARCH variance. Enter. So a new series is generated. Again, I'll go back in the model, and this time, let me close this. This is a GARCH variance series. This is your model. Again, I'll go in estimate, and now I'll change the model and I'll make it to arch model. I'll include 6 arch terms and no GARCH terms. So there are 6 variables in the model. 6 terms are there in arch family, and the GARCH family has been made with 2 terms. Click OK. And you got the result. You can see here there is no GARCH term. All arch terms are present. Again, I'll go in proc, make GARCH variance series. I'll name this as arch variance. Click OK. And I got the series. So now I'm having arch variance series and GARCH variance series. I'll open both the series together. So for this, I'll close this and I'll go from arch and GARCH variance, open as group. Now I want to compare the variance of both the series. So view, graph, click OK. The thing which you should observe here is that the variance of both the series are overlapping. But the advantage in GARCH is we are only using 2 terms, while in GARCH we can achieve this volatility with the help of 6 terms. So arch and GARCH variance has same conditional variance, but the GARCH produces similar results with the parsimonious model. It means that with lesser terms in comparison to arch, which is a over parameterized model. So just imagine that to get the same effect, arch has to include more terms in comparison to GARCH, which the same effect GARCH can produce with less number of terms. Now there is another model which we can include is GARCH-M mean model. GARCH-M model allows the conditional mean to depend on its own conditional variance. Consider for an example investors that are risk averse and therefore require a premium as a compensation in order to hold a risky asset. That premium is clearly a positive function of the risk. More the risk, more the return. If the risk is captured by any volatility or by any conditional variance, then the conditional variance may enter the conditional mean as a function of yt. In my original mean equation, yt is equal to c plus xi ht. So ht is a riskiness of the security, which I am saying that my return should increase by the xi times plus mu t. So GARCH-M mean here, the more return we'll get in yt is directly proportional to the xi times of ht. We are taking the square root here, which is also known as the riskiness of the asset. Or if the risk is captured using standard deviation of the series instead of variance, so we use yt is equal to c plus xi square root of ht plus mu t. So there is a question from the investor. What do I get if I take risk which is equal to the volatility, more the volatility, ht? So the answer is you will be rewarded in mean return by the amount equal to xi times of the conditional variance. Now, what is the change in the equation? We will have to see. The equations of the GARCH-in-mean model are shown as yt is written. So the new term which has been introduced is theta ht. Ht is the risk which the investor is taking. So we are saying that the return will be theta times of ht. This is the only change which has happened in the equation. Now let us see how we can carry out the same thing in EViews. For this, I'll have to go in the environment of EViews. I'll go in estimate. Now I'll keep this as 1, 1. And here, variance will be activated because I want to include the variance term in my mean equation. Why? Because this term will specify that how much risk I am taking. And on that basis, my return will change. This is the only change which is to be done. Go in options, make sure EViews legacy is on, click OK. And now you can see that in mean return, the GARCH term has been included. Now how to interpret this? Let us take this in the Word file. Now we will have to see the p-values of this GARCH term. In the mean equation, the p-value is more than 0.05 and this term is insignificant. So GARCH is captured in the mean equation. GARCH term is not significant in mean equation, but by including in mean equation, the variance equation has improved considerably. So by including in mean equation, it has improved the significance in variance equation. But we can interpret that the risk premium is not significant to hedge against the holding risk, as this value is not significant. It means that even if you take more risk, it will not give you the more return, as this term is not significant. If it was significant, then definitely this would have contributed in the mean return, but it is not significant. Now we can carry out this analysis. Again, we will go in estimate, and this time in options, make sure that you activate the standard deviation effect. Click OK. And you got the result. Let us copy this result again on the Word file. Now here you can see the term here is square root of GARCH. Again, the p-value is more than 0.05 and therefore this term is not significant. How will write the interpretation? GARCH term is not significant in the mean equation, but by including in mean equation, you can see it has improved the significance in variance equation. The risk premium is not significant to hedge against holding the risk. It means that the risk does not give more return. It means that if you take more risk, it will give you more returns is not applicable here in this model. Now there is one more GARCH model which is known as a threshold GARCH, also known as a GJR-GARCH. Here we assume that the news events, incidents have a strong influence on the decision making of the investor. This means that the financial markets are asymmetrical. They are having an asymmetrical impact. It means that the negative news effect is more on the volatility in comparison to the positive. So our standard GARCH considers that the positive mu t minus 1 is greater than 0 and negative mu t minus 1 is less than 0. The news have similar impact. The standard GARCH assumes it. But that is not the case. But we know that the negative news have a higher effect on volatility with respect to positive news, and therefore the markets are asymmetric. Basically, we run the tgarch to see that is there any asymmetry or not. So to include this effect in a model, a multiplicative dummy variable is introduced into the variance equation to investigate that whether there is a significant difference in volatility when the news are negative. The equation will change like this. Ht is equal to lambda 0 plus theta 1 ht minus 1 was always present, plus lambda 1 mu square t minus 1. The new term which will be added is gamma mu square t minus 1 dt minus 1, where dt takes the value of 1 for mu t less than 0 or otherwise. So good news and bad news have a different impact that we want to assess. Gamma is known as the asymmetry or the leverage term. Good news has an impact lambda 1, while the bad news has an impact of lambda 1 plus gamma. It's very simple. When the value is 0 and when the value is 1, what will be the effect? So we conclude that there is an asymmetry, while if gamma is greater than 0, this term is greater than 0, we conclude that there is an asymmetry, while if gamma is equal to 0, the news impact is symmetric. A very simple question asked, will good news and bad news affect my volatility with the same intensity? The answer is normally bad news impacts volatility more than the good news. Now, how to carry out this in EViews? Let's go in the environment of EViews. I'll go in estimate. Make sure threshold is 1 and this should be none. And in options, the legacy option should be on. Click OK. And you got the answer. Now directly copy this output in the Word file. Basically, you will have to see the p-value of this term. So let us take this in the Word file. Control A, copy, OK. Now let us see the value of this term. This one, which is basically the asymmetric term. It is positive and it is less than 0.0. P-value is less than 0.05. So what we will interpret, variance equation indicates that the coefficient of asymmetry term is positive and statistically significant, which means that there are asymmetry in the news. Bad news have larger effect on the volatility of the stock in comparison to the good news. So what will be the equation for the positive stock? The estimate of time varying volatility is given by. So if we say that gamma is equal to 0, this term is completely absent. Now 1, 2 and 3 terms will be there. 1, 2 and 3 terms will be there. So my HT is equal to 0.0064 plus 0.954 HT minus 1 plus 0.014 sigma mu square T minus 1. Now when I take this term value equal to 1, I'll get this also included in the variance equation. And therefore, in case of negative shock, my equation will be HT is equal to this term plus 0.954 as it is plus 0.014 plus 0.051, the asymmetry term into mu square T minus 1. The difference between good news and bad news on the return is 0.051. This is an additional thing which is there, which is a coefficient of asymmetry term. So the gamma, that is the bad news, have a larger effect than the good news. Why? Because lambda 1 plus gamma is greater than lambda 1. Still, another model in the GARCH family is the exponential GARCH. It was developed by Nelson in 1991, where gamma, zeta, and delta, that is xi, gamma, delta, xi, and delta are to be estimated. Note that the left-hand side of the equation is a log of the variance series, log ht. So here we are taking log of ht. This makes the leverage effect exponential instead of quadratic, and therefore estimates of the conditional variance are guaranteed to be non-negative. Gamma is constant, zeta is arch effect, Xi is an asymmetric effect, and the delta is GARCH effect. The egarch allows for testing of asymmetries as well as a threshold GARCH. To test for asymmetries, the parameters of importance are Xi. If Xi1 is equal to Xi2 is equal to 0, then the model is symmetric. When Xi is less than 0, then the positive shocks generate less volatility in comparison to the negative shocks. Let us see how we can carry out this in EViews. For this, we will have to go in the environment of EViews and estimate. And from here, we will have to activate egarch. Keep everything as it is and run the model. In options also, check it. EViews legacy should be on. Click OK. And you will get C3, C4, C5, C6. C3 is a constant term. C4 is a arch coefficient. C5 is asymmetric coefficient. C6 is GARCH coefficient. The equation is already given to you here. Now let us see how we can interpret this thing in Word file. Copy, Control A, copy to the Word file, click OK. Now let us understand how to interpret this. C3 is constant, C4 arch, C5 asymmetry. Basically, we are interested in this part. And C6 is a GARCH coefficient. The coefficient of C5 is negative, minus 0.0442. It is statistically significant at 1% level. In exponential terms, when I'll convert this Xi, it is e raised to minus 0.044. Now, why this conversion is necessary? Because our dependent variable is running in the log scale. To interpret anything, I'll have to convert all these things into, by using exponential, I'll have to convert it. So e raised to minus 0.00044, I'll get the value 0.6428, which indicates that the bad news has a larger effect on returns in comparison to the good news. So the total leverage effect is if mu2 minus 1 is less than 0, the total effect of mu2 minus 1 on lag ht is 1 minus Xi, modulus of mu t minus 1. That is negative. This value is negative. If mu t minus 1 is greater than 0, the total effect of mu t minus 1 on log ht is 1 plus Xi, 1, modulus of t minus 1. The next model is the integrated GARCH. We know that for the stationarity, alpha 1 plus beta 1 should be less than 1. But if it is greater than 1 in any scenario, if alpha 1 plus beta 1 is greater than 1, so we call it as an integrated GARCH process. It's an iGARCH. This means that the volatility coefficients of the arch effect and the GARCH effect are both positive and their sum is between 0 and 1. But in integrated, see, we require that the summation should be 1 according to the theory. But if any case, if it is more than 1, we should go for integrated GARCH process. Now, how to carry out this in EViews? Let's see. We'll go in estimate. Make sure this GARCH is on 1, and the restriction which we have to include now is iGARCH. This is the restriction which we have to introduce. Click OK. And you can see here, now we have got the estimates based on this iGARCH. Similarly, you can now interpret according to the previous way. Now we will carry out some diagnostics on this model. You can see now the summation of both this is between 1. Basically, it will correct the model, and therefore we are imposing the restriction on the model. Model is selected on the basis of list number of parameters which are there in the model, significant arch and GARCH coefficients, high adjusted R square, high log likelihood ratio, lowest squads information criterion, no heteroskedasticity should be present. This is tested with the help of arch LM test, White or Bruce Pagan test, Bruce Godfrey test, and no autocorrelation. This is detected with the help of correlogram. We will carry out this analysis in EViews. I'll again go in estimate. Make sure arch11 is on, returns is on. This is kept on non. Normal Gaussian distribution is kept on. Click OK. You can see here arch and GARCH terms are significant. Right. Now we will carry out the residual diagnostics, view residual diagnostics, and here arch LM test. Make sure arch effect is on, click OK. You can see here the p-value is more than 0.05, and you can say there is no heteroskedasticity in the residuals. The null hypothesis in this test is that the residuals are homoskedastic. Alternative is residuals are heteroskedastic. Here, the p-value is more than 0.05, therefore we fail to reject null hypothesis and we conclude that the residuals are homoskedastic. Again, we will go in view, residual diagnostics, and correlogram Q statistics. Legs to include 36, click OK. Again, you will see that the p-value of all of them is more than 0.05, and therefore we can say that there is no presence of serial correlation. View, residual diagnostics, this time correlogram squared residuals. Click OK. Again, you can see that the p-value is more than 0.05, therefore there is no serial correlation. Now you can carry out this test by changing the error distribution to students T. Click OK. Now again, you will go in view, residual diagnostics arch LM test. Click OK. And we found here that the p-value here again is more than 0.05, and therefore residuals are homoskedastic. We'll go in view, residual diagnostics, correlogram, Q statistics. Next to include 36, click OK. You can see here that the p-value is more than 0.05, and therefore there is no serial correlation. Again, view, residual diagnostics, correlogram squared residuals, click OK. P-value more than 0.05, quite good. Now we will repeat the same procedure for different error distribution, which includes generalized error, students with fixed degree of freedom, GED with fixed error terms. Now these models will be compared on some criteria. This is an error distribution term which we are including. Normal distribution, students T is GED. R significant, R coefficient significant, are arch terms significant, or is GARCH term significant or not? What is a measure of log likelihood? Adjusted R square, squash criterion, heteroskedasticity, and autocorrelation. Your log likelihood value should be more, squash criterion value should be less, and therefore this model is appropriate. Once we have confirmed that the error distribution is following students T, basically we will have to carry out the analysis on all this distribution, and we found that students T error is following the students D distribution, and on that basis we will estimate the model again and click OK. Sorry, we will have to make sure that egarch is kept at non. Click OK. We'll get the answer. Now we want to forecast this variance. For this purpose, I will have to go in the window of forecast. The forecast is done for the full sample. Therefore, I'll make this as static forecast. Click OK. You can see here returns are quite stable. But here asset shows the intense volatility. Now I will do the forecasting for subsample. So I'll go here in forecast. I'll change this to 99. Click OK. I'll have to change one setting. Instead of dynamic forecast, I'll have to go for static forecast, and I'll have to make this as 99. Click OK. And you can see here that the returns are stable, but assets show decrease in the volatility. You can see that a decrease in volatility at the end of the year. For more videos on econometrics, kindly subscribe to my channel. You can follow me on LinkedIn and Twitter.